Let's think about this. For an aircraft in flight, we know pretty well that there are four main forces. Well, the number one, this is weight going straight down vertically, and weight equals mass times gravitational acceleration. In order for aircraft to fly, we need an equal or larger force into the opposite direction, which is called lift. The lift formula we will learn in problem 3 and repeat in problem 5. Now, in order to propel the aircraft forward, we need thrust. And experience tells us that the thrust comes from the engine, so I attach this one here to the engine. Thrust. And thrust is opposed by a value called drag. We will deal with that one in P4, problem 4, drag. Thrust and drag have business with each other, they balance each other. If thrust is more than drag, the aircraft would accelerate. If thrust equals drag, it would remain a constant speed. And if drag is bigger than thrust, the aircraft would decelerate. If lift and weight go into relationship, then lift equals weight would cause the aircraft to maintain its altitude. Larger lift and weight makes the aircraft climb. Lesser lift and weight makes it descend. Lift and drag don't have a direct relationship. Thrust and weight do not have. Lift and thrust do not have, and drag and weight do not have. So the relating forces are weight and lift. They belong together. Drag and thrust belong together. Now we can look into a situation where an aircraft is in climb. Now many of us think that the aircraft climbs because the engines push it upwards. And that's not so far-fetched, because when you look at this, you can draw a line which basically represents a horizontal line, the horizon, or just the surface of the surface of the Earth. And you can draw a line which represents the longitudinal axis of the aircraft, and you see it pitches up, it points its nose into the sky. Now we know that we have the thrust coming from the engines, pointing this way. Now this is not perfectly horizontal, and we can assume that there's a vertical component of thrust as there is a horizontal component of thrust. So I want to call them H and V, vertical and horizontal, for simplicity, while this one is my engine thrust. Now, doesn't this horizontal component, this vertical component, make the aircraft climb? Let's quickly take a look into basics of trigonometry. We have a triangle, and this triangle sports a 90-degree angle down here, 90 degree. Now we know if we have a situation like this, we have one long side of the aircraft. I call this H for hypotenuse. And we have two other sides, which we call cathetus. One is adjacent to an angle alpha here, so the adjacent cathetus would be here. I call this A for adjacent cathetus. And we have the other one here. I want to call this O for opposite. Opposite cathetus. And from secondary school maths, we remember one formula which is the sine of our angle alpha equals the length of our opposite cathetus divided by the length of our hypotenuse. Or we can change this a bit and say, if we do not know the opposite cathetus, but we know the angle alpha and we know the hypotenuse, then we can write our opposite cathetus equals the length of the hypotenuse times the sine of the angle alpha. I guess we remember all this, and with this knowledge we go back to this aircraft. Now we go here and we see we have an angle alpha. That means our vertical thrust component, the one which would lift up our aircraft, equals our total thrust times the sine of our angle alpha. Now let's assume, and there's a bit agar-agar here, let's assume that alpha equals 12 degrees. I put nose up in brackets here. We will later learn what this is good for. Let's assume this is an Airbus A319. The two engines would provide for a thrust of 39 kilonewton each. Two engines, that means 2 times thrust equals 78 kilonewton. Please do not forget to carry along the units of measurement. Now we can continue to use this in order to figure out what is our vertical thrust component, the one which is lifting up our aircraft. It is the thrust of 78 kilonewton times the sinus of 12 degrees. Sine of 12 degrees is about 0.1, so I continue in black to simplify my writing. So V equals 78 kilonewton times 0.21. There's no dimension here, and that equals, well, I should say that is approximately 16 kilonewton. Now we remember we need to lift our weight. The weight of our A319 calculates as mass times gravitational acceleration. The mass of the Airbus is about 60 tons in this landing configuration. So my weight is 60,000 kilogram times, I take a rough number here, meters per square seconds, which equals 600,000 Newton or 600 kilonewton. Now when we put these two into relation, we figure out that our thrust component provided by the engine is only about 2.5% of our weight or of the lift we need to make the aircraft fly. That's not convincing. Now let's go extreme, let's go broke. And let's look at an aircraft like this, which is truly in a takeoff configuration just after takeoff, just after liftoff. We draw again a line representing our Earth surface. We draw a line representing our longitudinal axis of the aircraft. And we figure our angle alpha would be here. And I claim alpha is 25 degrees, which is pretty much what you see in an aircraft in the takeoff. So from previous calculation we know that our vertical thrust component, this is a capital V by the way, equals our total thrust, 78 kilonewton, times sine 25 degrees. The sine of 25 degrees is rather large. You can find this out. So our vertical component is 78 kilonewton times 0.4. Sorry, 0.2, which is approximately 33 kilonewton. And we remember our weight was 600 kilonewton. This is the minimum lift we need. And again, the amount of lift we can generate from our angled thrust vector is only about 4.6% of the lift we require. So we're still missing 95+% of lift, and we have to look into P03 and P05 to learn how to generate